this the right way. It's really good. Some z is equal to 0 and be free to move around.
All ready to go? All right, thank you.
That's cool. And then this one's like an orbit thing.
Yeah.
I'll take a picture of this. Sure. I kind of want to do some of these. Were your other tests take home?
We had one.
That was taken on one that was in class. But the one that was in class was pretty hard and no one did very well on it. Oh shoot. So I don't know if he's even counting that one. What was the topic? There was just one problem. And it was like a Lagrangian, but it was like a spin state of magnetic field. Oh shit. Like you get really harsh on the grading. Like you have to explain everything. So
All right, is the audio at school mic okay?
I can hear you.
All right, kids. All right, so I think I haven't got everyone's final homework, but if you're still wrapping it up, send it by the end of the day. So this is the last lecture, and there's no final exam. So this is really the end. Or really, what it should be is the beginning of the end of your, very minor introduction into quantum field theory. Because, right, it seems like we went over a lot, and we did, but that is because it was necessarily condensed. But really, this is scratching the surface of all that there is in quantum field theory. Which is also why I didn't want to do a final exam. I wanted to make it clear that this is not like a normal class, right? This is, an ongoing story. We don't know all the details of quantum field theory yet. If you normalize your expectation to sort of normal quantum mechanics, where maybe you could learn it in a week or something, quantum field theory really, to get a basic understanding, takes a full year, and we haven't even done that here. So there are a lot of other topics you could study. There's a nice book, I think I mentioned in the syllabus, but there's a book by Anthony Z, which is just called Quantum Field Theory in a Nutshell. I think that's probably the best thing to look at if you want to just get a sampling of different topics. I mean, it has a huge number of topics, and none of them are that in-depth, but it gives you a flavor of what's going on. So it's a very, very helpful book in that sense, to give you sort of a bird's eye view of a lot of topics, and then, depending on your taste or interest or, what seems the most confusing, however you want to think about how to organize where to spend your time, that's a really good jumping off point. And then Peskin does a pretty good job of diving into more details. And then also this more recent book by Matthew Schwartz, which is called Quantum Field Theory It's called An Introduction to Quantum Field Theory and the Standard Model. That's a really good textbook that sort of combines a lot of even more advanced topics than either Peskin or Anthony Z's book. So let me just start out by giving us a little bit of an overview and talking about a little bit more about the Standard Model too than what we've said so far. And of course there are a lot of things not in the Standard Model, so maybe that's worth also mentioning. So let's just talk about sort of our path that we followed in the class. And I'll talk a little bit about these steps. But what did we do at the very beginning, right? So at the very beginning of the class, we sort of pretended that you already had a class on classical field theory. So no one did. Maybe we should start doing that. But we had a review, not really a review for most people probably, of classical field theory. So this is sort of our chapter 1. And this was helpful, right? I mean, we learned some things like Noether's theorem and stuff. But then we took basically our, so I forget what they're called, the canonical, our standard variables are the equivalent of our position and the momentum conjugate to position, and we promoted those to commuting variables to do what's called canonical quantization, right? This was of a free field theory. So we turn on quantum mechanics, but really just focus on non-interacting things for starters. And then we turn on interactions, but in particular, we're sort of careful about how we turn on interactions. We do so that we can use everything we derive from field theory, free field theory, with just small perturbations. So by interactions, we really mean small deviations from a free theory. We turn on interactions, which are really perturbations of free theory. So far, right, with each of these blocks, right, it was a couple weeks on each of these topics, right? Then after we got a little bit of a glimpse of interactions, we looked at things like phi cubed theories and phi to the fourth. And then we want to make things more realistic and turn on spin and go back in a certain sense. We looked at the classical Dirac-Lagrangian. Then we had to go back, basically, right? Because in a sense, classical field theory was all classical scalar field theory, really. So in a sense, we went backwards, back to classical field theory, but now with fermions, which, after spending some time, eventually quantizing, we got to quantum electrodynamics, which in a certain sense is sort of the summit both of the class and also field theory. I mean, it's in a sense, one of the best achievements of quantum field theory, right? It's this amazing agreement between theory and experiment. If you look at, say, the anomalous magnetic moment for the electron, right? There's this amazing agreement, however many decimal places it is. And from quantum electrodynamics, we sort of took things in two parallel tracks from there. One direction, which is a whole huge topic, and most of what constitutes a second semester, is we looked at renormalization. And in particular, your final homework was doing one important calculation for of a topic of, one important explicit calculation involving renormalization for quantum electrodynamics, this vacuum polarization. And the other important generalization is from quantum electrodynamics. We started to see with the view that Yang and Mills had about the importance of gauge invariance is that really gauge invariance seems to be pretty crucial, pretty fundamental to all interactions. It helps us understand, in a certain sense, where the photon comes from in QED. So then we want to generalize that beyond just abelian theories and go to non-abelian, go to what's called Yang-Mills theories. So this is a very brief sort of broad outline of the various topics we covered. So if any one of these seem unclear, we should talk about it, or also, you should know where to go into Peskin to find an answer to your question. So let's just talk about really quickly too, a little bit more about what were the important things we found out in each of these topics. So in classical field theory, we started to develop an idea of, it's classical, right? So let's think about what are important things in classical physics. Basically, equations of motion, right? That's sort of the heart and soul of classical physics. So we had to learn about the Euler-Lagrange equations. So let me say this is for sort of step one, classical field theory. So those most important topics, for sure, were the Euler-Lagrange equations for fields. So maybe that's a new thing. So it might be a good idea if in the future that instead of requiring in graduate curriculum that we learn how to do a whole semester or whatever it is for non-field classical physics, but not involving fields. It might be helpful if we devoted at least some amount of time to classical field theory in such a class, because it really is sort of a helpful way to build some intuition for what goes on in quantum field theory. We also learned how to think about Lorentz invariance, fields, and their Lagrangians. And maybe the most important thing, which became sort of a thread that we followed throughout this whole path, was the importance of symmetry and Noether's theorem. Remember, that's a classical thing. It happens to be upheld in quantum mechanics too, but Noether's theorem we could already start learning about in just in this classical field theory introduction. If I have a symmetry of the Lagrangian, I also get out a conservation law. So there's a really high weight given to symmetry in field theory, even at the classical level. So that was classical field theory. Were there any outstanding questions from classical field theory? So then we started, things got a little messier, for sure, when we start turning on quantum mechanics. So we started out just talking about the Klein-Gordon field, or just a normal scalar field. And the first important result that we used was that basically free Klein-Gordon field is really just a set of simple harmonic oscillators. And that was even exact, right? It's no longer exact when we turn on interactions, but assuming they're small, we can still use this formalism, and we definitely did, right? That was basically the approach we took throughout the rest of the class. So we also started to see the importance of causality I mean, this is an important thing, right? We don't want no, if we don't want any information leaking out of a light cone. This gave us some ideas of what kind of propagators we were allowed to make. Right, that was really the most important final result in canonical quantization is what is the propagator for a scalar field. We got out the scalar propagator from that. And also started to think about these funny integrals, right, where we can write the Feynman propagator, right, as this four-dimensional integral where you have certain prescription for how to do the contour in the complex plane. But that was a technical detail. So for canonical quantization, right, the other I should stress probably, but right, these involve commutation relations. So some commutators for scalars, right? Remember when we went back to classical Dirac and tried to quantize there, you can't use commutators. That was a big deal. We had this inconsistency. You have to use anti-commutation relation. So that was canonical quantization. And then interactions is a huge, important part of quantum field theory. There's a lot of important results in that chapter. So definitely stop me if there are questions along the way. So the first thing, right, is this idea, right, very, very important is that interactions are small perturbations. A free Lagrangian. And inherent in that, right, we made a little bit of a big deal about it at the time, is that what does small mean, right? Does it just mean having some small coefficient? It sort of does, but it's also, what we mean by small depends on the energy too, because of the class of interactions, right? We focused at the end, and we have in the back of our mind, because of the importance of quantum electrodynamics and the rest of the standard model, they all work with renormalizable interactions. But there's no theorem that the world has to only use renormalizable interactions. I mean, in fact, right, our first insight into the weak interactions was not through Yang-Mills, but through a non-renormalizable interaction that Enrico Fermi wrote down. And it's a correct description, it just doesn't work at all energies, but it's perfectly fine at low energies. So what we mean by small is a bit subtle, right? So we have this classification of marginal, relevant, and irrelevant interactions, where marginal and irrelevant have this strong energy dependence, but marginal interactions are, in other words, what are called renormalizable theories or interactions, and those happen to be the ones that the standard model obeys. But anyway, so small, right? Even, really, I think, yeah, interactions may be the most important part of the first semester of quantum field theory. There's a lot in it. What do we even mean by small? And how do we compute? The propagator, right? We want to basically understand interactions. We can try to lump everything into the propagator. Say, how do we take initial state I and turn it into final state F? Well, we want to solve for what the propagator is, and we could do that from solving the Schrodinger equation. And Dyson told us that the consistent way to do that in quantum field theory is with time ordering. And that was a big important thing. Dyson's time ordering formula for the solution of the propagator gave us a perturbative series, right? He gave us the exact solution, it's an exponential. That thing isn't so helpful by itself, but it's helpful term by term. Gives you a way of figuring out, if you're interested in whatever process, to whatever order, it gives you a prescription for how many terms you need to include in the Dyson expansion formula. That'll tell you how state I turns into final state F. And what was really helpful for us is that on top of Dyson's formula, there was a guy, Wick, who told us how to turn a time ordering into a normal ordering, something a little more computationally helpful. Right, this is basically how to turn time ordering into normal ordering. And then finally, after these really old guys, Dyson and Wick, had written these important papers, this young upstart guy, Feynman, came along and said there's a much cooler and easier way to do these sorts of steps with just drawing nice pictures. Which are the Feynman rules and diagrams. But we can always go back, if we need to the old-fashioned Dyson formula and Wick's theorem. And really, this is sort of the proper way to derive the Feynman rules, right? For the most part, we weren't very rigorous about deriving the Feynman rules, how we associate the pictures with explicit calculations, but you can get it from these two ingredients, from Dyson's formula and Wick's theorem. And ultimately, the reason that these tools, of course, were helpful is because at the end of the day, they tell us how to calculate, again, this propagator, just how we turn one state into another. We stopped referring to the propagator, but that's basically because we took some limit. Time initial goes to minus infinity, and time final goes to positive infinity. And everyone is an eigenstate of the free theory asymptotically, and we defined that object to be the amplitude. So then after that, we stopped talking about propagators in this sense, right? We talked about propagators in the Feynman diagram sense. But the thing that tells us how we go from one state to another, that's all encoded in the amplitude. So that's how we got our quantum amplitudes, which ultimately gives us almost every observable you can think of, right? It gives us decays, cross-sections, etc. Decays and lifetimes are, of course, the same thing. So it gives us, I guess a better way of saying it is that it gives us also the total lifetime of a state, and it also tells us the branching ratio. What specific decay modes are allowed for certain particles. All of that's encoded in these amplitudes. So you can see why, interactions really, this is really sort of the heart of the class. The first time we turn on dynamics, see how particles can fall apart and turn into other things, and how different scattering processes are allowed or not allowed, and so on. So right, interactions is super, super important. Are there any questions about the interactions chapter? Outstanding questions? So then, really there was another chapter, I guess, after classical Dirac, where we did quantized the Dirac field. And I'll talk about both of those sort of together. So there's really a baby step in between, but classical Dirac and quantum Dirac. but maybe it's helpful to think of us just sort of repeating the same path that we followed before. And that was really exactly what we did. This is just sort of chapters 4 and 5. So first thing was, right, how do we know the electron, for example, had a spin 1/2, but how do we start writing down a Lagrangian for an electron, even without interactions? So we needed to know an important thing, which is how, so we say classical and quantum Dirac. The first thing was, what is the Lagrangian for a Dirac field? Even classically, this led us to start wondering about things like how do spinors transform under Lorentz invariance? What is the spinor representation under Lorentz invariance? And we had a little detour to various general representations of the Lorentz group, which helped us build up the spinor representation. And also, when we were talking still just about classical Dirac fields, talking about chiral spinors. So we put together, we group the left and right fields into one, we call them U plus and U minus. Group them together into one 4-component Dirac spinor, and that's what we call a chiral spinor. These guys separately can become uncoupled if there's no mass. If it's just a massless field, and that can work separately with these states, which were called Weyl fields, or Weyl spinors. And we also mentioned even in the classical introduction that there's another type of mass term you can write down, also that's still Lorentz invariant, which is the Majorana mass term, which you can't write down for anything in the standard model except for the neutrinos. But we don't know the source of anything having to do with the mass for neutrinos yet. So we also, when we turned on quantum mechanics, we found out that fermions need anti-commutation relations, right? That was a big deal. And then the final, just like we had when we were doing free field theory for scalars, final important parts when we turn on quantum mechanics is figuring out what's the propagator for a Dirac field, and also what's the rule associated with incoming and outgoing fermion lines in Feynman diagrams. So basically, how do you do Feynman diagrams with fermions? And we also talked about the Noether theorems that will hold in the Dirac case. We saw that there was a global U1, so there is a conserved charge, which leads to quantum electrodynamics. So I guess I'll call this 6. It's 5. So you got more acquainted with quantum electrodynamics and also renormalization in the last problem set. But right, the way we finally started to think about quantum electrodynamics was from the idea of promoting the global U1 of the Dirac Lagrangian So someone who has no interactions, just a free theory, promote that to a local theory, basically gives you everything about quantum electrodynamics, which is no small feat, right? I mean, you get all of Maxwell's equations out of it, you get the proper interaction that fermions have with the photon field, and you get that the photon has to be massless. So there's quite a lot in that statement, and that's why we think now this is a big important thing. Local interactions, which also mean gauge theories. Sometimes people say this is a gauged U1 by making it local. So when we first encountered quantum electrodynamics, we also basically took the approach of let's argue by what else could it be for the Feynman rules. We didn't do a very rigorous job of deriving them, but we basically more or less stated with minimal justification the new Feynman rules, which were basically what's the photon propagator, and also what's the Feynman rule associated with the fundamental vertex of QED, which just has to do with using a gamma matrix and a charge. So we already could have started, when we first turned on interactions, we could have already started talking about renormalization. We waited until we saw quantum electrodynamics to do that. So basically, all until this path, when we got to QED, we were always doing tree diagrams. We weren't allowing any, except for maybe a small detour or something, we weren't really calculating any loop processes. But we saw when we do that, we sort of have some problems. A lot of times you'll have infinity for an amplitude. And so that was the procedure for how to deal with that has this weird name, renormalization. Which basically just means for renormalizable interactions at least, maybe I didn't stress that enough, or in our previous nomenclature, this is what we called marginal theories, ones who have interactions with mass dimension 4, meaning that you can describe their interactions with dimensionless coupling constants. For relevant and irrelevant, there's a mass scale associated with the theory. But for marginal theories, can basically absorb infinities into the definition of a coupling. The way that this worked is that we said we wanted to define a coupling as an observable. And that lets me sweep an infinity under the rug and still have a huge amount of predictivity. So I can still, if I define my coupling to be basically the scattering amplitude that you get when you scatter particle 1 and 2 at some energy scale, that allows me to make predictions for what the coupling will do at a different energy scale, with the main important result being that couplings run. Couplings run or change with energy scale. And that's a huge topic. There's a lot of technical machinery that goes into ways of regulating those infinities, basically ways of just isolating the infinity, because once you do the renormalization condition, and absorb away the infinity into some definition of the couplings, it's very convenient to have all of those infinities nicely isolated from the important stuff, the stuff that's going to be finite. And so all of that machinery goes in renormalization, and those techniques having to do with regularization too. Just different ways of dealing with the infinity, either through a cutoff, introducing some fictitious particle, or imagining you live in a different dimension of space-time where the thing isn't infinite. So those different techniques. So you learn a little bit about dimensional regularization in this last homework. So this is a very big topic. You could certainly spend the whole other semester just studying this. And the proof that standard model gauge group is renormalizable took a very long time to show. And that was a Nobel Prize awarded, I think, in sometime in the 2000s, but for work done in the 70s or so. And then the final big topic was Yang-Mills. This really started from the idea that gauge interactions, or gauge symmetries, I should say, I guess, seem fundamental. And so what happens when we go beyond just a simple abelian theory like we have for QED? What happens if we consider gauge interactions that are non-abelian? This is basically what's meant by Yang-Mills. So this is, of course, very important for understanding the electroweak group and also for understanding the strong interactions. And for understanding the electroweak group, like we discussed, there's this important detour beyond just Yang-Mills, which is about spontaneous symmetry breaking, because the electroweak group seems to not be totally preserved. For the strong interactions, all the messenger fields are massless, so just like the photon, we can talk about a preserved gauge symmetry, but it's not the case for the electroweak gauge group. But those are the highlights of what we discussed. So I was maybe going to also try to write down the full sort of standard model Lagrangian, since we didn't do that, and talk about the fields that are in it and how they transform under the different symmetries, just as a way to sort of cap the class. And we can also talk about things that are not in the standard model. But are there any questions about the main topics we've talked about? I'm sure there are, but it may take time anyway to think about more and digest. Or
one thing with the fermions needing anti-commutation relations,
right.
I never quite wrap my mind around what that really means. Is there like a good analogy?
Well, so ultimately, physically, right, it really directly leads to the exclusion principle, right?
Yeah.
So it has that deep physical
Right.
consequence.
Yeah.
So that's one.
Is that really the fundamental theorem that why, like the real theorem is the exclusion principle and then the...
No. So, I mean, we can't, so it's a consequence.
Yeah.
The exclusion principle is a consequence of the anti-commutation. But the important thing was that we found, we didn't want anti-commutation relations, right? It was that we couldn't. Things were inconsistent.
Right.
So it's just that if we want a spin one-half field to still, have all the nice features of quantum theories and not spoil things like causality, then there's no way out. You cannot use commutation relations. Yeah. So that was really the path. And then the consequence of having anti-commutation relations is the exclusion principle.
Yeah.
Yeah. And anti-commutating things may play a more fundamental role in nature, we don't know. They've at least shown up once in the real world. I mean, fermions are definitely real. They really seem to be anti-commuting in that sense. And there could even be other symmetries beyond the sort of Lie group type symmetries that we've talked about that all obey commutation relations. There may be symmetries, so this is a different type of anti-commuting thing, symmetries that obey anti-commutation relations. And those are nothing like the Lie groups we've talked about. They're what are called supersymmetries. And another thing that makes people think that they maybe have a deeper connection to the real world is that their anti-commutation relations, if I just think about, building on what I know about Lie groups, I just have some generators in Lie groups, right? And they obey some commutation stuff, and I get back another element of the Lie group, right? If I want to generalize that to something anti-commuting, it basically has to be like a spinner. So the generators themselves, I don't know why I'm playing the QED. So this is really for supersymmetry. If I want to have some anti-commuting type of symmetry, then the generators themselves have to be spinners. And the only way for that to really work out is for the right-hand side of the anti-commutation relation to involve a space-time or a momentum generator. Yeah, one of the fundamental symmetries of space-time. So it seems it's a weird type of symmetry. It seems to have a sort of a generalization of the Lorentz group embedded in it. Just from considering anti-commutation, just considering an anti-commutative generalization of Lie groups. So people think maybe supersymmetry will help us learn something more about space-time or about the Lorentz group, in addition to being the only type of symmetry that will transform a scalar into a fermion. So it's possible there's still more to learn about anti-commuting fields. So let me say a little bit about a standard model, a little bit more, and ideally let's try to write down everything about the standard model, right? At least to have it in one place. So the ideal setup, from the point of view of the importance of gauge symmetries, and also of Lorentz invariance, right? It all is coming back to symmetries at the end of the day. The invariance of the Lagrangian under the Lorentz symmetry and the invariance of the Lagrangian under the gauge symmetry, where someone has to tell us, unfortunately, the gauge group of the standard model. That's something we don't understand. But if you're given that information, right, if you're given basically the charges of some set of fields, in this case, I guess, the standard model, you can get the total Lagrangian, consistent with Lorentz invariance, right? So this is a very basically the most minimal set of information someone would need to give you in order to write down the full Lagrangian. So all you need to know is what are the charges of the different fields of the standard model under the standard model gauge group. So our, like we talked about, gauge group of the standard model is this thing, SU3 color, SU2 left, and U1 hypercharge, and that thing's spontaneously broken. But before it's spontaneously broken, let's just talk about what are the charges of all the fields under those three things. Also, what are the fields I need? We didn't really talk about that either. And then we can see how spontaneous symmetry breaking goes through. So what are the fields? So in a sense, what I mean by what are the fields of the standard model, what are the non-gauge fields, right? Because this information encodes what are the gauge fields. Right? I don't need to specify those. I basically just need to specify the matter fields of the standard model. So let me write them down, and I'll also describe some notation for what we mean by them. So the left-handed quark field, so the fact that this thing operates only on left-handed states is not understood. You'll know why. People have built theories where maybe standard model comes from a bigger gauge group where also you have SU2 right, which is spontaneously broken some higher scale, and that's why we don't see its effects. But we don't know right now why it is. But it seems that we can describe what's going on, for example, when for things like the decay of the neutron by promoting the up quark and the down quark into one doublet of SU2, one two-component doublet. And this field transforms under these interactions. So again, right, all I should need to tell you are the charges. You should be able to get everything else out. So it's a triplet under SU3. It's a doublet by construction, like I'm saying here, under SU2, and its hypercharge is 1/6. So, this is our notation. I write down everyone. Write down all the charges. So this means that there are 3 left-handed quark fields under SU3. That's because there's a red, blue, and a green one of them. That's the names we give to the charges for SU3. It comes in a 2-component doublet for SU2, and the value we assign to it under hypercharge, this is just a number, right? This is different in a sense than the other two. These are sort of telling you how big the dimensionality is of the state, but this is just a number. And the way that we know the hypercharge is from, this will also be something sort of in parentheses from last time, right, is that we get the electromagnetic charge. After electroweak symmetry breaking, we talked about the fact that the residual preserved U1 is a linear combination of one of the generators from the original SU2 and hypercharge. So we can determine what the hypercharge is of a given state from just looking at what are the electromagnetic charges that are associated with that state. So you can check, for example, right, that this would give you, so for the upper state, T3 is 1/2, and for the lower state, it's -1/2. This is the third generator of Pauli matrices. So you could find out that this gives you, that this is a plus 2/3 state and this is a minus 1/3 state. We also have to have, basically now that I've explained the notation, it's easy to write down everything else. We also need a right-handed singlet quark state. So it's singlet under SU2. That's someone who's still a triplet under SU3 color, but a singlet under SU2. So he's not paired together with someone else. He just transforms trivially under SU2 of the weak interaction, and he has to have a hypercharge of 2/3. I have also a right-handed down quark, which doesn't do anything under SU2. He does still transform just the same way under SU3, and he has to have a hypercharge -1/3. And you can basically copy the same sort of structure for the leptons. So I also have to build a left-handed lepton state out of a neutrino and an electron. This is something that doesn't transforms trivially under SU3, which is just a statement that leptons don't talk to gluons. They do talk to the weak interaction. This allows me to see a neutrino, for example. It can come in and scatter on a nucleus or something and convert into an electron through the exchange of the W because it talks to the weak interaction. And has a hypercharge -1/2. And the thing that's a little asymmetric about leptons and quarks is that so far we only know that there's a right-handed component for the electrons. We don't know if there's a right-handed component for the neutrinos. The right-handed electron state is a singlet under SU3, a singlet under SU2 of the weak interactions, and has a hypercharge -1. So we don't know, but there could be a right-handed neutrino, which would be a singlet, and no hypercharge. So this is certainly not observed, but would be an obvious thing to maybe think about existing. It would, for one, make things a little more symmetric between the quarks and the leptons, right? So this is enough information to give you everything for the Standard Model, right? You can now basically, by just looking at things like those covariant derivatives, right? This is our minimal coupling procedure. We take a kinetic term for any of these states and convert their ordinary derivative into a covariant derivative under these gauge charge assignments, and we get out their interactions with the gauge fields. So that's what I mean by this being sort of the minimal content to get everything from the Standard Model. And also, the other way that we say we construct Lagrangians now is we're forced to write down any renormalizable interaction between these states and themselves. So there are also Yukawa interactions I can write down, for example, between quarks and the Higgs field, that, for one, allow the Higgs field to interact with the quarks, but also will give them masses when electric symmetry is broken. We didn't talk about that, right? We focused on how the Higgs mechanism gives masses to the two of the gauge bosons of the electric symmetry, but they also give masses to the fermions, which are also not allowed until electric symmetry is broken. So with this minimal information, right, we can write down the full Standard Model Lagrangian. It consists of terms like all the information about the electroweak interaction, all the information about quantum chromodynamics, the Lagrangian associated with the Higgs, and Yukawa interaction between the Higgs and the Standard Model fermions. And I can get all of those ingredients, all of the specific terms in those sub-Lagrangians just from this information. So we could write that down briefly. Are there any questions about this or about the notation?
And the three generations are just...
Oh yeah, sorry, I didn't say that, right. There are indices, so basically for everyone here it's times 3. That's right.
And is that just that we know of? There could be more?
Yeah, that's right. That's right. There could be more. So 3, we don't know why there's 3 generations. There could be more. There are dedicated LHC searches for 4th generation. The limits, I'm sure, are much better on 4th generation quarks, since they would be colored. The LHC is colliding together colored objects. But yeah, the limits are at least TeV, if not tens of TeV, on a 4th generation And for certain assumptions, probably even better than that. All right, so let's try to write down the first of these ingredients. Actually, let me write down QCD first. That's sort of the purest thing to write down because there's no spontaneous symmetry breaking. Oh, and I guess I should say, right, this is the high energy Lagrangian, right? So I still, because of the content of the Higgs sector, will have spontaneous symmetry breaking, and then this electroweak Lagrangian will, include as part of it quantum electrodynamics, along with the interactions with the W and Z bosons, which have masses after that. So for quantum chromodynamics, for the strong interactions, so I'm going to have the same thing written down multiple times for any of the states which transform non-trivially under QCD. So any of the ones that have a 3 in what we wrote before. And again, right, the nice thing, maybe I should say, nice way to derive most of those interactions, right, is just to do this. Well, in particular, to derive the interactions of fermions with gauge fields is promote normal derivative to this gauge covariant derivative. And then, right, I think of starting out with the Dirac field and just make that replacement with the Dirac Lagrangian. So the Dirac Lagrangian is this psi bar I gamma mu now times the derivative. And not going to, the normal kinetic part of the derivative isn't going to change one quark type into another, but it will allow me to rotate one type of quark into another by interacting with a gluon with a certain coupling, which also we can't derive, unfortunately. So this is the interaction, and then I have masses. And a kinetic term for the gluons. Let me just highlight what these things mean. Right, this is the coupling constant with the subscript S for strong. These are the SU3 generators. They're the equivalent for SU3 of the Pauli matrices for SU2. They're called the Gell-Mann matrices. And this is the gluon. This is an 8-component gluon field. So this just says one of those triplet of quark states for all of those sides, right? This could be up, down, bottom, charm, etc. Anyone who has a 3 in what we wrote before, they come in groups of 3, a red, green, and a blue, and the red, green, and blue can be rotated into each other through this gauge interaction, through a gluon. So this is this psi I. This is a Dirac spinner for the quark field. And that index I mean, yeah, in real life you don't use RBG, but you use 1, 2, 3, but we'll use the more prosaic name, red, green, and blue, since they're color interactions. So and that's the whole story for quantum chromodynamics at the Lagrangian level, because everything's preserved, there's no spontaneous symmetry breaking, that's all that there is. So things are pretty similar for the electroweak interaction. Pre-symmetry breaking. So again, have some psi bar gamma mu I times derivative minus now two different gauge couplings. Let me write that as sigma. And kinetic terms for W bosons and also for the hypercharge. Where now this so G prime is the gauge coupling, the U1Y gauge coupling, and this is the SU2 coupling. So two separate couplings, and each field can have a different hypercharge assignment, like we wrote down earlier. So that will tell you how much each of the standard model fermions, how strongly they interact with the hypercharge field, which will go in to become part of the Z boson and part of the photon. Then the final two charts of the standard model Lagrangian are the Higgs Lagrangian, which we basically have already seen. But we didn't discuss the fact that the Higgs is basically a doublet itself. So when I write down the kinetic term for the Higgs, I should do it with a gauge covariant derivative, so it has a hypercharge assignment and also it's a doublet itself. So all that acts on phi, predict that whole thing absolute value squared, and the other part of the Higgs Lagrangian is lambda phi to the fourth part, which I can rewrite. So the mass term, I can rewrite all of the Higgs potential in this way, where basically this will give me, let me write what V is, right? V was U squared over lambda, the vacuum expectation value after spontaneous symmetry breaking. This is just a different way of writing the Mexican hat potential, along with the kinetic term for the Higgs. Where Higgs itself, the way I wrote phi here, is itself a doublet. That includes an electrically charged Higgs state and a neutral one. And to give us normal electromagnetism, I have to have that only the bottom component gets a vacuum expectation value. This is the would-be Goldstone boson associated with the breaking of the symmetry that gives mass to the gauge bosons. So it's not a physical state that survives. And if he got a vacuum expectation value instead of the lower component, we would break electromagnetism. So we don't want that to happen. And the final thing we can do with the states, maybe I should have included Higgs along in the charge assignments before. Higgs is certainly not charged under SU3, so there's no SU3 interaction that would show up in this gauge covariant derivative. The final thing I can do, again consistent with just wanting things to be Lorentz invariant, gauge invariant, and renormalizable, or in other words marginal, there are dimension 4 interactions I can write down between this standard model Higgs field and my quark doublet. So this is invariant under SU3 because I basically have a 3 and a 3 bar. So it's going to be invariant under SU3. It's also invariant under SU2 because I have a doublet and a doublet bar. You can check that the hypercharge assignments worked out so that this is flying under hypercharge 2. And I have another interaction along the same lines for the down course. And these are nice. I mean, for one, they're required, right? I don't have any say in the matter if I'm writing down all possible terms in the Lagrangian consistent with Lorentz invariance and gauge invariance. But it's also nice because once the vacuum expectation value is turned on for the Higgs field, now my quark fields acquire a mass. Oh, sorry, there's of course also one for the electron. Don't know why I forgot to do that.
Is that a QD bar?
Yeah, here? Yeah. So another downside though with these interactions is that, right, there's no one tells you the value of the couplings except you measure the masses and can verify that these couplings are consistent with what you get from the masses by looking at things like how often does the Higgs decay into a pair of bottom quarks, for example, something like that. So those are all the interactions, basically, of the Standard Model, right? Gives you everything, in principle. There are a lot of parameters you have to just measure, right? Basically all the masses, or equivalently all the Yukawa couplings for the fermions, you have to just go out and measure. No one gives them to you. Yeah, the gauge couplings also we have to measure, again, at some scale, basically, in order to specify how they're going to run. We have to define the coupling at through some observable, basically. So one thing that stands out, right? So when we started talking about interactions, right, we had this breakdown, again, marginal, relevant, and irrelevant. So one attitude about the Standard Model might be to say, non-renormalizable interactions aren't necessarily so bad. Enrico Fermi made some progress with the weak interaction by just writing down by fiat a non-renormalizable interaction describing how a muon can decay into an electron and some neutrinos. He just wrote that down. He didn't know about W bosons, right? So maybe there are things we can just write down with Standard Model interactions, even if they're non-renormalizable, that might help us explain some of the gaps of the Standard Model. And so, there's an infinite set of non-renormalizable terms I can write down, but there's only one that's of dimension 5, which is a little strange. So with this field content, there's literally only one interaction, and that's the one that maybe can explain neutrino masses. So now maybe I'll say a little bit about things beyond the Standard Model and also existing questions of the Standard Model. There are two things you could think about when wanting to go beyond the Standard Model. One is, what do we know we have to go beyond, just by force by data, things like neutrino masses. And then another line of questions you might have are just questions about the Standard Model. Why 3 generations? Why certain couplings? Things like that. So right, one of the most outstanding questions that already you saw just writing down charge assignments is why aren't there right-handed neutrinos, right? That would explain neutrino masses, which are also the only particles, right, when we wrote down the Yukawa terms with the Higgs boson, that's the only thing we couldn't write down a mass term for. So the prediction from the original way that the Standard Model is written, which is what we just wrote, is that neutrinos should be massless. But they're not. They're definitively not, based on oscillation measurements. So So we don't know what that comes from. That comes from something beyond the standard model. But like I was saying, one line of reasoning to explain where neutrino masses came from, well, there are two, right? One would be, let me posit some right-handed neutrinos, and then I can just write down an interaction. Another is to say, let me use, say, the power of effective field theory that helped Enrico Fermi, and just write down a dimension 5 interaction. And there's really only one that I could do with all of the fields of the standard model, and that's to say I take a lepton doublet and a Higgs field, and a lepton doublet and a Higgs field. And there's only, this is totally gauge invariant and totally Lorentz invariant, and it's the only interaction like this that's allowed at dimension 5. What's nice about that is that I know Higgs gets a VEV, gets a vacuum expectation value, so then I would predict that I get a neutrino mass that's at 2 VEV squared, right, times, or divided by this unknown scale lambda. Lambda is just the scale of whatever it is. That's the new standard model, right? Non-normalizable interactions have to have this new mass scale. So it turns out, right, if I want to explain, let's say, 0.1 EV masses that we seem to need from oscillation data, this scale needs to be something like 10 to the 14 GeV, something maybe not too far from our sort of grand unified scale where proton decay might happen. This could also come about from just right-handed neutrinos. Since they also allow for pilot interactions with the Higgs. Or I guess I should say 5. That's what we were. And it turns out, actually, if I take this right-handed neutrino mass to be really heavy, I can essentially integrate it out in the same way you can integrate out the W boson at low energies and get just the effective interaction. And if I do that, I actually get this operator, this dimension 5 operator. So these are, in a sense, equivalent. I mean, this is more general, the dimension 5 statement. But if I take the mass of the right-handed neutrino being large, I get the same interaction. So they're sort of complementary approaches. You know, if this right-handed state is really living at 10 to the 14, it's very, very hard, if not impossible, to see experimentally. But there's no requirement more generally. You know, I don't have to use this operator to get the right masses. I could have right-handed neutrino states that are much lower also. So another thing we know that standard model doesn't have, it doesn't have a mechanism for why there are so many more baryons than antibaryons. That's a pretty big outstanding question. All right, we need something that violates baryon number, and the proton is very well protected in the standard model. Doesn't seem to be any source of baryon number violation. So there has to be something that gives rise to this in the real world. Also, we know most of the matter in the universe, right, is invisible. And most of the energy in the universe is invisible. These are probably the biggest phenomenological bits of evidence in favor of stuff beyond the standard model, maybe dramatically beyond, right? Things like dark energy may take many, many, many years for us to understand what it's coming from. I mean, at least that's sort of my bias, is that these other three, I think we have a better shot at understanding in the near term, whereas dark energy I'm a little less hopeful about. But then we also have questions just like, you know, these are sort of, in a sense, these are data-driven questions. No one, you know, basically we're forced to have dark energy because of CMB data and supernova data. We're forced to have dark matter, we're forced to have baryogenesis, and forced to have neutrino masses, all from direct data. There are other questions which are basically internal to the standard model, things like why are there 3 generations? That's one of the biggest ones. Why do we have SU3 color and SU2 left? The hypercharge. Why do we have this as the gauge group of the standard model? And is there a theory of couplings and masses? These are just things we have to put in. So these are sort of, in a sense, these are internal standard model questions. So in the immediate aftermath of the construction of the standard model, these questions were the ones looming largest, and people especially focus on number 6, why this gauge group, and tried to explain it by positing a bigger gauge group that had spontaneous symmetry breaking, something like SU5 or some bigger group that could give us the standard model gauge group. So again, the sort of upshot is that quantum field theory has done a pretty good job, right? It's 3 out of 4 of the fundamental forces of nature, but there's certainly a lot to be desired. There's certain questions it doesn't answer, and certain things we know we need to extend, at least the standard model. Maybe not quantum field theory itself, but we need to extend the standard model at the very least to accommodate major important observations in the universe, things like neutrino masses and dark matter. And we may live to see what the next thing beyond the standard model is. We just don't know. I mean, at one level, it's nice that neutrino masses are pretty easily incorporated, but disentangling what's correct is another issue, right? I mean, disentangling from data whether or not it's really some rather low-scale right-handed neutrino, or someone living up at 10 to the 14, that's very hard to do right now. Yeah, it really depends on the model. So we'll see. We'll see. Are there any questions about the class, about quantum field theory, or the standard model? All right, if there aren't any questions, then I hope you had a good time in the class. I hope you're glad there's no final. But that really just means, the final exam is really up to you, right? I mean, it's really an open-ended class. It's probably the last major sort of class for many of you, normal classroom class. But now then you start the transition into not getting knowledge out of the textbook, right? But figuring out your own path, right? Which is sort of the point of how I wanted to present things, right? This is a really ongoing discussion with quantum field theory. So hopefully we'll live to see what goes beyond.
Thanks.
All right, thanks. And turn in your final homework if you haven't yet. Don't forget that. That's effectively the final exam.
Thanks for semester, Dr. Schreiber. Happy holidays.
Yeah, thanks. Happy holidays to you too.
और भी छोड़िए थे
Oh, walk and talk. Actually, which way are you parked?
What's that?
Which way are you parked?
That way. That's it. See ya.
Yeah, see ya.